Hello, I am Bradley Sward, Associate Professor of Computer Information Systems at the College of DuPage in Glen Ellen, Illinois. And this video today is part 3, the last part of a 3-part series in which we're looking at object-oriented programming in the C++ programming language. So this video is taking a look at inheritance, polymorphism, and virtual functions, all the more advanced stuff. So if you need a recap, I have 2 other videos getting us up to speed with data hiding, encapsulation, operator overloading, constructors, and you name it in the other 2 videos. So I already have, because I know where we're going with this stuff today, I already have this going for point 1D, because we're going to be taking a point in 1D space. This is, so just think of the number line, the left to right horizontal number line, and we're just going to maintain a class called point 1D that maintains a specific point on that number line. It's basically a wrapper for a double. So I'm going to have a value that's being stored under the hood. I'm going to call it x because that's going to be the x coordinate on the one-dimensional line. And then we're going to have the constructor that sets it up. So you have to supply a value for what goes into that when I start out. I have a get function, I have a set function, and then I have this distance to origin. And so as I know, 1D is going to be different than 2D, which is going to be different than 3D and all of that stuff. So I know that I have a function called distance to origin, and coming over to the implementation of that, it's just the absolute value of x. Whatever value, just how far away from the origin point am I? If I'm negative, well, it's just a magnitude. So I just strip off that negative if I have to. So my constructor goes ahead and sets up this value using an initializer list. The get just returns, and the set just sets. And I think we're ready to go. I think we're ready to push forward. Just make sure you have this in 2 separate files. I already have my source, but I don't have anything going with it just yet. But I do have, again, everything is set up over here. Let me move the source.cpp over here for now. Pretty small stuff here. And now we're ready to talk about inheritance. How do I take this point 1D class and go, hey, there could be a 2-dimensional object? And how do I do this the smart way rather than the think smarter, not harder kind of thing? So the first thing we have to do then is take a look at what is inheritance? What is this idea we're trying to get across before we even think about putting it into programming code? So inheritance, what we're going to do today is providing a way to create a whole new class that uses an existing class as a template. So when we do this, when we set up our point 2D class, we're going to basically get much of this functionality for free, and so we can actually start using this as if it were our own, and then we can go ahead and create because we're going to need specialized versions of specific things. Specifically, we are always going to need a specific constructor for a 2D object because the behavior is different than a 1D object. And we're also going to need different behavior for this distance to origin because the distance from the origin point for a 1D object is going to be different than the distance to origin for a 2D object. And so, thinking about this, I kind of alluded to this in my previous video, that like a banana is a fruit, an orange is a fruit, and it's 10 o'clock. Okay, 1 second. And so in this case, they like to use this insect example where they say that all insects have certain characteristics. One of these days I'm going to look up, at least name one of them if you're going to describe, but it's one of those things we pretty much know an insect when we see it. Like I said, there are always there are always kind of issues when it comes to categorizing things. Especially, don't get into like, is a cucumber a fruit? Is a tomato a fruit? It's like let's not worry about those little details. But we can understand that a grasshopper is an insect. We can understand that a bumblebee is an insect. Even though this one flies, this one jumps, there's completely different characteristics about them. There are enough commonalities where they can be grouped into the thing called insect. And so we're going to have the same thing. There's enough commonality here where we can say, okay, point 1D is basically the insect here, and point 2D will be the derived class from that, or something that something that derives from this idea of insect. And this is where the idea of the is-a relationship comes from. So the grasshopper is an insect, the bumblebee is an insect, and then we'll set it up so we'll say like point 2D is a point 1D. So that kind of stuff here. So again, here it is. Poodle is a dog. Car is a vehicle. It's that is-a versus last time at the end of last lecture, I was describing a has-a relationship, an aggregate class setup, where the cylinder class had a circle as part of its member. This is different that would be saying, can you say that a cylinder is a circle? And I can't agree with that because it has a circle and it does stuff with that, but it's not like, I would say a sphere is more like it because you could take a circle and rotate it, and essentially you're just taking a circle and turning it into a 3D space. Okay, so advancing this out, we have our base class, 0.1D, and we're going to have to fix this up a little bit over time, so I'm going to come back. So hopefully, again, you have this written out. You kind of have it working for you. And so the 0.1D, since we didn't plan ahead, but like normally you would plan ahead for this kind of thing if you knew what you were getting into. But since we don't have 100% understanding, we have 0% understanding. So then right now I'm going to go into describing how to set up the 0.2D and start working from that. And you can kind of see that here in this slide. So let me just go ahead and set up the 0.2d.h file, the header for this thing. Okay, and there we go. And so now what I need is, just like before, I say, okay, let me set up a 0.2d. Let me just put the public and private stuff in here. Okay, and then we need, just like you see here, we need to tell the compiler that we are going to derive from another class. And so you have to watch out for this. First off, you have to do the include file. But you have to watch out. This language is different. You have to put the word public up front here. And this happens to everybody, me included, especially if you're flying through different languages over the course of a day. Why is this not happy? Oh, there, okay. And because if I don't put this public, it doesn't work like you expect. You won't be able to access the members like you think you would be able to, and such and so forth. And you don't do this in other languages, so it can be complicated to find that mistake when all you did was forget the word public here. Because you could have public inheritance, protected inheritance, private inheritance. It's complicated, and I don't know 100% all the reasons why you would need all those kind of details. But this gets everything going when it's, at least on this slide, of showing up and saying, okay, I'm going to have a class called 0.2D, and I am going to be using 0.1D as my base class. And so the getX, the setX, and the distance to origin functions have come along for free. They're not here, but I can use them, and that's pretty cool, right? So we can show this in a future slide. And so now we're ready. We have to create our own constructor. We'll have to create a Y value because the 0.1D is perfectly happy as it is. We're expanding 1D, so we're going to have to do that here in 2D, and then we're going to have to change up what distance to origin means and maybe add a few other bells and whistles, odds and ends as well. So let's talk about this is-a relationship one more time because it is very, very important. I mean, I'm not just wasting time talking about it because it's the foundation for everything that's going to come, especially when we start using pointers and virtual functions and things. This is the very important part. So as I was just saying, the derived class is an object of the base class, and this will come in when we start using collections and things like that. So anytime I can say, oh, like I said, I need a fruit, I can replace that with a banana. I can replace that with an orange. So I can replace any 0.1D with a 0.2D, and everybody's going to be happy because essentially there's a point sitting in front of me. And so the power, the coolness comes from the polymorphism, and you'll see that as we get there. So an undergrad is a student, a mammal is an animal, and again, the derived class, this is not necessarily true in the real world, but it is in computer science. The derived object gets for free all of the characteristics of the base class. And so the child inherits everything that's public and everything that's protected. That's a new one here. We have public, we have private. Coming back to the 0.1D, should I be able to access this X value inside of anyone who derives from me? And the answer is probably a yes, because I'm probably going to need to do stuff with that X value as if it were my own. And that's where there's going to be a new one here in a slide or two. It's called protected, and in a minute I'm just going to change this from private to protected. So everything that's public will come along and I can use here, and everything that's protected I can come along and use. But just like anything else, whatever is private in 1D would stick around and you wouldn't be able to use because it's private. It is very specifically only usable by 0.1D. And so constructors don't come for a ride, destructors don't come for the ride, and everything else can. So you have to watch out. So it's like you have to just learn the rules. You have to know like which functions do I have to do, which functions don't I have to do. Okay, so again, protected is this new class here. And so there's, oops, coming back here, there's no reason, I don't like the protected keyword personally, but that's just me. But now by changing this from public to protected, this is now saying, instead of it being just me, anybody who derives from me can get access to this thing and use it as if it's their own, because you are technically, it is you, if you want to think about it. You're just using this as a base, and you're plugging in little cartridges to use, so you should be able to access that if you want to, as opposed to the outside world, who theoretically has no understanding of what's going on under the hood. And so no, you wouldn't want them to just go ahead and just go inside and just change data without thinking about it. So that's the whole idea. So this is protected, the double X, and everything else can stay public because it's, you know, that public is as accessible as you can get, but protected is a pretty good way to go about doing this here. So here are the three ways. Public is everybody, private is just me, protected is just me, and anyone who derives from me. And so they have all these things that just kind of go ahead. And so the rule of thumb here is, you can always put more security on. You can take a public, and as you're working your way down from point 1D to point 2D to point 3D and beyond, you could add security. You could turn a public function into a protected one. You could turn a protected function into a private one. But you can't reverse it around and say, oh, you are private, well now you are public. Because that would be hacking at the programming level rather than hacking at the hacking level. And it's because you could just say, oh, I don't like the fact that that is private, and then just create a derived class from it, and then just go ahead and change what you want to change anyway. I mean, that's the reason why this is, that you can go and make things more private, but you can't make things less. And so all these slides just to show that kind of stuff. Okay, so now putting it all together, we discussed that, you know, when it comes to at least constructing and destructing these objects. And so when it comes down to it, again, these three functions came for free, but I can't just create a point 2D object. I can't, you know, like without using a constructor that can also construct the 1D portion of this, because I still need to, under the hood, construct my X value. Okay, so derived classes must have, or they can, but to be functional, they must have their own constructors and destructors. And when okay, so here's the rule here. When an object of a derived class is created, so when point 2D is created, the base class constructor is executed first, and then it works its way down. So it's a very strange little thing here. You would think I'm creating a point 2D object, but what you're doing is creating the object from the inside out. You're taking, and we're going to create the point 1D portion of this first, and then we're going to go ahead and tack on and instantiate the 2D portion of this stuff. And then it's reversed on the other way around. When I'm destroying the thing, it's almost like a stack operation. The point 2D will destroy itself first, and then the point 1D will destroy itself afterwards. So when it comes to construction, it goes base to derived. When it comes to destruction, it's derived to base. And so they have this kind of stuff. Let's add on what we need to add on here, and then we can add the functionality. So what we want to do for sure here is, okay, and we can make this protected now when we've discussed this idea, because who knows, I might create a 3D point, and so, or 4D if this is physics. If we're talking string theory and we go up to 10 dimensions or however many dimensions string theory is, maybe we have a 10-dimensional point. Who knows, right? Okay, so I definitely want to keep track of a Y value, right? I never spell double right these days. And so we have that going for us. I'll need a get function and a set function. Let me see if I can just steal this from over here. Yeah, let's just steal this from over here. I'm going to need an X value and I'm going to need a Y value now. That my constructor for point 2D is going to need that, right? Because I need two coordinates. And this time I'm going to say get Y, set Y. And then I can override this distance to origin function. And so this pretty much looks very similar to what you see here in point 1D, right? Very similar stuff. It's just a matter of, well, what's going to happen is the point 1D portion of this object is going to maintain the X, and then the point 2D part of this is going to maintain the Y, and they're both going to work together in peace and harmony. Hopefully peace and harmony. So they have this base class, constructor, destructor, and stuff like that. And I still contend we do not need a destructor for either of these. Well, we'll get to the whole point 1D part. And let me just put it in now. We will need a destructor for point 1D. And I'm not filling it in 100% correct. If you know what I'm doing, you know I'm not doing it 100% correct just yet. And so there I have my Destructor on the 0.1D side. I do not need it on the 2D side. And so, okay, so they've got their stuff going. And so what we're going to do now is we're going to set up the constructor. And so we need to talk, the derived constructor needs to work with the base constructor so everybody sets up everything correctly. Remember, my #1 rule for constructors is you have a contract to set up all the member variables of all the different types you are obligated to set them all up to something valid by the time the constructor ends. So I need to make sure that the X gets instantiated. I need to make sure that the Y gets instantiated. But it's a little more complicated because now I'm dealing with this whole structure. So let me go ahead and set up all these functions. And there we go. And where's my 0.2D? There we go. Okay, so now how are we going to set up? Let's just do the easy stuff here. Get Y, return Y. Set Y equals value. Distance to origin, this is a little different here. We can use the hypot function, and we could just say x comma y. I'll just need to include CMath for this. Hypot is part of the 2011 standard that just gives me, if I give you an x and a y, it'll give me the diagonal. That's what I want, right? So there we go. So all these were relatively simple, and notice, again, coming back, that this distance to origin function is different. The name is the same, it returns a double, so the signature is the same, but it returns a completely different function in itself. Absolute value for 1D, the hypotenuse of a two-dimensional shape in the 2D form. And we'll go, this is the prime definition of a virtual function, and we will fix this up when we get to that point. Okay, so last thing to talk about here when it comes to the constructor is the fact that I have a compiler error. No default constructor exists for class 0.1D. And so we were discussing that I have to set up the constructors such that everything gets initialized. So I am 0.2D, which is a 0.1D. I have to follow the rules. I have to supply a 0.1D constructor that's valid. And the only one that's valid is the first one we have here, where we pass in an X value. And so notice we can't, how would we even do this, right? How would, you would say, oh, I'll just use base, or I'll use super, depending on the languages that you're familiar with. Those do not work here in C++. We have to use an initializer list. And the first thing always that you have to do is, because it's the first thing that does happen, is I have to call the parent the base class. And so I have to supply 0.1D, and then now I have to supply, you see here, IntelliSense is telling me I'm going to supply the X value up the chain, because the 0.1D portion only needs that one value as part of its constructor, as you can see here. This 0.1D needs the X value to come on in and set. And so that handles the 0.1D portion. This constructor will call over to here and do this work and then come back, and then it's up to me to finish the job and to say, okay, my Y is going to be equal to my Y value. And there's still nothing here. And so that's why the initializer list is so important. If you have to use it anyway when it comes to using base classes and derived classes, then why not just use it all the time? Plus, it's more efficient and more professional anyway. Don't you want to be more efficient, more professional, so you can show your work off and get a better job? Just to show that you know more about the language than other people. And so that's exactly where we're going with. So they have square derives from rectangle. You can see that, and so they call up they call up the chain. Square takes one parameter, and then it brings it up and turns the rectangle into two, because a square is just a special rectangle where all sides are the same. And so we showed here, if you do not have a default constructor for the 0.1D class, we must call something that is not a default constructor, because it was trying to use the default, but since we defined one here, the default fell away, because that's the whole point of default, is it's a placeholder. And so we've done everything right so far with the understanding that we have of setting up the constructor, setting up these functions, and we still get access. We still have access, public access to all three of these, and we can, and we'll see later, we can actually access this version and this version of distance to origin. But we definitely get access to x values, set and get. We get access to y values, set and get as well. All right, so before I worry about using these, just real quick here, constructor inheritance. In a derived class, some constructors can be inherited from the base class. You'll just get the experience of understanding how this all works. But this is the basics of just taking a number of parameters, deferring to the base class whichever parameters you need to push up the chain, and then filling in the gaps with everything that needs to be done on your end. And so as it shows here, the constructors that cannot be inherited are things like this: default constructor, obviously, copy constructor, move constructor. All those specialized ones are very specific to your class and nothing else. So if you need more behavior, you would have to define it on your own. And so coming back, let's start using these things. So I can just say, okay, just to see, I can include point 1D .h, and I can include point 2D.h. All right. And I can just create a point 1D object, which is 7.0. I'll use negative just so I get used to it here. And I'll use a point 2D object called B, and I'll supply negative 3.0, comma 4.0, something like that. And we don't have any print statements or anything like that, but we can see if I do a dot, you can see this A is a 1D object. I get access to the destructor because it's public, set and get for x, and distance to origin. So yeah, I get everything I would expect. So this should print out a dot distance to origin 7, right? Oops, I gotta. Okay. And so, but what about, and so if I did that, and I did the same for B, I hope that I get 7 and I get 5. And I did. That's perfectly legitimate. That's perfectly fine. So that's so that's what we want out of this. But look at now B dot, and you see all the cool stuff. When I did A dot, I did not see anything when it came to any derived classes because I'm not deriving from anything. I can only talk about what I am, and point 1D is only point 1D. But point 2D is also point 1D, so it got all of the functionality. It got the x values and the y values. I'm sorry, the get x, the get and the gets are together and the sets are together. But you have get and set for the x, get and set for the y, on top of just one distance to origin function. And so we're doing pretty good here. So that's the whole idea. We're working our way toward inheritance. And so we have, in essence here, we have redefined. This is not virtual functions. This is not polymorphism. All we've done here is set up and said we've redefined these base class functions. The function in the derived class has the same name and parameter list as a function in the base class. And it does, because it doesn't take any parameters, both of these things, right? They take no parameters, they return a double, and they do different work. That's perfectly fine that they do more work, but the signature itself, outside the fact that this is point 1D and this is point 2D, are exactly the same. And so this is used in this kind of case where we're going to replace a function in the base class with a different, more custom version in the derived class. And so again, this is not ideal, and we say I can definitely show you a few examples once we start including the whole idea of pointers. And so we're going to be using pointers. So just to say that this is not best practice. It's not the same as overloading. It's not the same as virtual functions. This is called redefining. So because with overloading, the parameter lists must be different, right? When I'm overloading like an absolute value function, like I'm kind of doing here, like I would pass in an int in one situation, a float in another. That's different than this, where the signature is identical, but the behavior is different. In that case, generally speaking, with overloading, that the types are different, but the behavior is the same. And so in this case, as we know this, if we know we're dealing with a base class, we'll use the base class version of the function. If we're using a derived class, we'll use the derived class function. And so It gets a little complicated moving forward, though. So they have, notice they have a set score, which gets overridden. They say they have a whole nother example here of using the same kind of stuff. And as long as you keep it simple, like we've done so far here in the main, you will never have an issue with this. But again, why not be more professional? Why not do it the right way? And the way that'll get you the job is we're pushing forward here. And so the problem with redefining is, let's see what it says. So class base x defines function x and y, and x calls y. So the derived class inherits from base class and redefines y. Okay, let's just stop. You can see that the compiler can get confused. So like when you're calling x and calling y, how does it always know which one to call? And that's the confusing part of this. And when you're doing things like this at compile time, it's not always going to work out perfectly fine when you go to do this at runtime. And so, okay, we're getting closer to this understanding of what we're trying to accomplish. But right now, again, with redefining functions, right now you would say there's no issue with anything we've done, and technically there is no issue with anything that we've done. So it's not uncommon to have many layers of classes set up, like you see here. Right now we have class 1 or 0.1d, which derives 0.2d, and then maybe we'll do 0.3d here. I mean, we'll see how long this is taking us. And it's probably a pretty good example for repetition's sake. But, you know, it's not uncommon out in complex systems, 6 or 7 levels deep. You try not to go too deep. There's all the software engineering practices that you're trying to obey when you're trying to work this out, but it's not uncommon for this kind of stuff to occur. And so you could see something like this, graded activity. There's a final exam, which is a graded activity. There's a pass-fail activity, which is a graded activity. But there's a pass-fail exam that is a pass-fail activity, which is a graded activity. And so, you know, we group these things. That's what the whole idea of kingdom, phylum, and class and all that stuff, and, you know, genus and species, that's the same kind of idea where there's 7 or 8. I forgot if they added a new one. But there's all these different hierarchies. And so we could have, you know, just like from a video game, we could have just a generic game object. And then we could have like a skeleton, which derives from game object. And then we could have fire skeleton and water skeleton and what, you know, just the different types of skeleton classes. And then maybe you even have specialized versions of water skeletons and stuff like that. And everybody can derive from everybody else, basically steal the code that makes them that base and then makes things more custom for the things that make them more custom. All right, so here we go. Here's the idea of polymorphism and virtual member functions. So again, the reason why this, I can kind of push you toward the reasons why this doesn't work out for us. So what's happening here is everything is being determined at compile time. Whenever I see a value type, or even when I see a reference type a lot of times, this is all being done at compile time. But the reality is, what if I set up a collection of data? Let me just set up a vector here. Okay, so let's set up a vector. And this time we'll say 0.1d. And I'll call it points. And so in this case, I can say points.pushback A. And I can do points.pushback B. Nothing wrong about that. I can get rid of this for a moment. And so here we go here, and we're like, okay, I have a collection of 0.1ds, and you're screaming out, what the heck's going on? Why can't I put 0.2d into here? And again, that is all coming back to this is a relationship. The fact that I have a vector of 0.1d objects, but because the is a relationship, I'm allowed to interchange and put anybody that derives from 0.1d in its place. Just like if I said this is my hand is a vector of fruits. And so you can be like, here's a banana. There's no such thing as fruit, right? You can't just put just a generic fruit in my hand, but you can put a banana and an orange and an apple and so forth and so on, and that is interchangeable. You would not deny that you have a handful of fruit, a collection of fruit in your hand. You just have different types. And it's the same deal here. As long as I can derive and safely access 0.1d from where I am, then I'm legitimately allowed to be part of this vector. And so yes, now I have 2 points in here, but now this is where everything starts breaking down. And so if I said for every 0.1d inside of, or point1dp inside of my points, print out, I should have kept that, I got rid of it, but print out the distance to origin. And I'll put it with a space. And then maybe put an inline. Okay, so let's run this and see what we get. And you're not going to get what you want to get, because before we got 7 and 5, right, for our outputs. And this time we get 7 and 3 for our outputs. And you're like, what is going on? And so it just comes down to the fact that the compiler did its best to figure out what was going on at compile time when this is a runtime decision. There's no way that your compiler could possibly know on an item-for-item basis exactly what's sitting there under the hood. It's impossible. Because we notice there's a point1D object and a point2D object. They have the is-a relationship, but the only thing the compiler can tell you before you run your program and you start moving stuff around and start shifting things is that everyone here at least obeys the API for the point1D class. And because of that, we get static binding, compile time binding, to call the point1D version of the distance to origin for everybody. It doesn't matter who, because this function exists. And that's exactly what's happening. The point1D was fine because it's a point1D object, so it printed out the 7, the absolute value, perfectly fine. But then coming back, oops, I did this again. But then coming back here for the B part, it used the exact same function. It used the X parameter and applied absolute value to that, and now it returned a positive 3. And it didn't return the 5 because it didn't know to use the point2D version of everything. And so now we have to change our code up to allow this to occur so we can move away from static compile time binding and move ourselves over into dynamic runtime binding. And that's the whole idea of a virtual function, is to tell the compiler to change up the way that it activates and it uses and it determines what function to call at a given time. Okay, so the big paradigm shift here is that this is all now will be all done at runtime if I use the word virtual for the functions that could be modified. So like the gets and the sets we have for x's and y's, that realistically is never going to be modified and customized by anyone who derives from me. But this distance to origin, we already have done it. We redefined it. We have not made it a virtual function. And so again, redefining worked perfectly fine a minute ago, but now that I have a collection of this data, it won't fly pushing forward. We just proved it. So the virtual function is dynamically bound at runtime, and at runtime, it takes, every time you're going through this list now, it's going to look at each of the objects and go, hey, what type are you? And it will figure out exactly which of the point2D, or sorry, which of the distance to origin functions to call at the given time for each given object. Much more flexible, much more powerful, much more what we want this thing to do. And so coming back here, we can say, okay, I throw the keyword virtual in front of this thing, and once virtual, always virtual. And we also put the keyword, this is a newer one here, we put the keyword override here at the end and just in the point2D version, because override means exactly that. I am making a custom version of something somebody else has done, like the base class has made a version, and this is just telling other programmers that I have gone ahead and implemented a more custom version of this function. Okay, so there we go. We got virtual functions, and we go to make a function virtual, place the keyword virtual. You only put that in the header. And so once virtual, always virtual forevermore. You can't unvirtualize a function once you've made it virtual. And so that's why it makes sense just to kind of go sweeping through and just find all the places where you've done this and change and just put the word virtual in front. And so you can see virtual char get letter grade const. And so now the compiler will not bind the function, the compiler won't, the program will bind them at runtime. And it uses a whole different mechanism. There's what's called a virtual pointer table. There's a little more overhead. It takes a little more time for the computer to look at an object and determine, basically just kind of analyze it and go, hey, you're a point2D, and then know to call a specific function versus, hey, you're a 0.1D, which calls a different one. So there's a little performance overhead on that, but I think it's well worth it because you get all of this power and all of this flexibility to come with it. And so let's see. So by let's run this program, and you're like, oh, okay, I feel so much better about life. Don't read that slide just yet. But you get this, and you get the exact same results, and then you go, I need a new teacher. I'm calling the dean. What is Brad talking about? And now we finally hit the point where, like, this, what we've done up to now is correct. But now there is a second step. There's two things you have to do to get this thing to work properly. And it's unfortunate. It is very unfortunate that this language does this because it just adds unneeded complexity. And now the whole idea is I've done all the virtualness for this function. I've done it all correctly, but it doesn't work because I still have to use pointers or references, as this says, that the polymorphic behavior is only possible when an object is referenced by reference or by pointer. And so the PowerPoint slides kind of describe that, but we will have to fix this up on this other end as well inside of here to make this work. So if you do none of them, you get a redefine, right? That's, we redefine the function. If you do virtual on this end, but you don't use pointers on the other, you don't get the results you want. If you use pointers on this end and you don't use virtual, you don't get what you want. You have to put both together. I have to create virtual functions, and I have to use pointers over here on this end. And so this changes everything now. Now I have to have a vector of 1D pointers because I have to for the polymorphic behavior to work. So now I have to say, okay, point 1D, I can say address of A. Or I can say address of B. Or if I wanted to, I could new up this thing, new point 1, just steal this thing. Don't use the A part, but just say new point 1D, and there we go. So I could do that, and I'll have to say now that I've newed up memory, I'd have to go in and delete it later. But I'm saying like things get more complicated this way. I can go ahead and do this, and now put a new point 2D in with a negative 3.0 and a 4.0. And so now with this in place, I got to change this up. So this is point 1D pointer P in points. And then I got to use this to change this into arrow notation. All the fun there, right? Object-oriented this and object-oriented that. And now, because I've used a virtual function and I've used pointers, now I get the polymorphic behavior. And finally, I get 7 and I get 5. Because on a case-by-case basis, it goes through, and for the first one, it goes, hey, you're point 1D, go do the point 1D code. And it just does the absolute value of x, and it prints out 7. And so for this one, it goes, hey, you're point 2D. And it goes, oh, cool. You do the 2D version, and then we get the square root of 9 plus 16, 25. We get 5 out of the D. And so, again, that is the key to this. You need both. That's exactly why in C++ we have to describe pointers. And we have to use them. And up front, we're just like, they're just memory addresses. Well, they are. And to a lot of times, they're just memory addresses. But it's the key component to inheritance and then polymorphism, because without it, it won't work. And I just proved it to you. It's unfortunate. Very, very unfortunate. Okay, so what we show here is that if we're using a vector of base class pointers, we can use those base classes, or we can also use the derived classes. Again, that is a relationship. So we can put, aggregate types. We can put different types in there as long as they all can work their way back into this point 1D. And it can, because point 2D right here screams out, hey, I'm a point 1D. And that's exactly why you see here that you can have two different types. As long as this pass-fail exam can derive back into graded activity, I can go ahead and do this and then access it like anything else. And so, excuse me, goodness. Just to be on the safe side, since I'm newing stuff up, I should delete everything as I'm going. So again, the base class pointers and references only know about members of the base class. That's all there is. That's what it comes down to. But the fact that I threw the word virtual in front of it means that, yeah, I only know of 1D, but at runtime we'll determine what that means. And so redefined functions and derived classes will be ignored unless the base class declares the function virtual. So again, no matter which way I approached it, I had to do both. I had to do both things to make this thing work. So you can't use a base class pointer to call it a derived class function. You just can't. We already showed that we, talking this again, this is a very important thing, that you got to do both. You can't do one or the other. So we're just saying the difference, redefining versus a virtual function. This is redefining is static. Everything was compile time. And said, but everything when you're talking about a virtual function and polymorphism is runtime. So say a non-virtual function is redefined, a virtual function is overridden. So that's just definitions of things. Okay, so now the idea, I was talking earlier about the idea of the virtual destructor, or I needed to have a destructor for this thing. And it just comes down to memory leaks. Because 0.1D's got memory, 0.2D's got memory, and the compiler isn't caught on to the fact that you're Frankensteining all these things together. And I don't like the idea. It's a good idea. It's more than a great idea. It's required if you don't want a memory leak to make the base class virtual, the base class destructor virtual. And so you don't. And again, once virtual, always virtual. So the 0.1D is virtual. So every destructor that derives from it will be virtual as well. And so what will happen otherwise, it's again static versus derived, static versus runtime versus dynamic binding. If I don't have a virtual destructor, I will only destroy the 0.1D portion of my object. And so 0.2D will be left alone. It won't be destroyed. It'll be a memory leak. And that's not good, obviously. But if I make this virtual, this means that the compiler knows that there's more than one destructor it needs to worry about. So it'll destruct the 1D portion and the 2D portion, and if there were a 3 and a 4 and a 5 and a 10D portion of those as well. So you need to have a virtual destructor. And coming back, just saying, like when it came to the exception class, and I can go, let's see, can I go in there and go to definition? And you can see down here, all of this is just garbage, garbage, garbage. But when it came to the destructor, it's a virtual destructor because the exception class is the base for all of those other exception classes, out of range and bad alloc and you name it. And so because of that reason, it's virtual so that when you create your own or all the others are created off of that and they come and go or created and destroyed, you do not have a memory leak. So the whole point of virtual is to make sure that at runtime, the correct operations are performed, because at runtime, you know a lot more about what's going on with your specific objects and your pointers and your references than the compiler could ever figure out. Let's talk about a few keywords here. These are newer. I always say new. I said 2011 new, 10 years old, new now. The override keyword tells the compiler that the function is supposed to override a function in the base class. So again, it didn't exist till 2011, and I'm still kind of iffy. And I know they use that in C# and those kind of languages, but just understand that you can get away with not having it in here, because that's the way it used to be. But again, it's just to kind of tip off the compiler and tip off like any other programmers that there is a more custom version, because you don't have to override. If I didn't want to, if I just wanted to leave it alone, I could just leave it alone. And so in this case, yeah, it doesn't make much sense for me to not to leave, to change it, leave it alone here. And so override screams out, I did change it. That was just a word salad there. And so override anytime I take over, and that's why I didn't do it in the 0.1D version, because I didn't override anything. That is the default base behavior until someone comes along and says, I want something different. And so final means exactly that. That means that I've defined it this way, and now no one else can redefine it any other way. And so if I threw the word final in front of here and in 1D and I tried to use it in 2D, let's virtual final double, my goodness, right? You start up, what does the error message say here? Virtual is not allowed. Okay, whatever, right? There are rules, but if I tried to make a final version of this, anyone who derives from me and tries to redefine it will get a compiler error, because basically you're saying nope. And it's partly so that other people can't go ahead and kind of work around your code. It's kind of like almost hacking in a way, because it's like, oh, I can if I override this function, I could get this behavior, but it's something I know that you shouldn't really do. It's just something you're just trying to do because you're just trying to hack it. And so, yes, by doing that, you can go ahead and say, nope, nobody can derive her. Okay, so we'll talk about this abstract-based classes and pure virtual functions here in a couple 10 minutes. So now what I want to do here is create, before I do this, talk about this, create a .3D class, incorporate that just to get a little experience making this one more time over, and then take a look at the three classes and see what we can do to kind of create a better architecture than the straight up and down architecture that we have, .1D, .2D, .3D. And then when we have that discussion and we start figuring out how to better architect, this just falls in place. Okay, so what I can do here is just start setting up .3D. Add new item, .h .3D. Okay, and oops, there we go. Okay, so .3D is going to derive, class .3D is going to derive publicly from .2D. So we'll need to include .2D. And we've got our public stuff and our protected stuff. And this time around, we've got Z. We've got a Z coordinate. .1D had an X, .2D had a Y, and then the depth of it all is the Z value. So I'm going to need a get function, get Z. I'm going to need a void set function for Z. I'm going to need a function for a virtual function, right? Virtual function, virtual double for, what was the stupid thing called? Distance to origin. Okay, and then that's going to be an override. And we're going to need a constructor. I mean, it's very similar to what we've already done twice over in this lecture already. So I've got .3D. I'm going to pass it. This time I'm going to pass in a double for X value, a double for Y value, and a double for Z value. Okay, so there we go. So we don't need virtual on the Z portions, the get and the set. We didn't need them for X's and Y's because we're not going to redefine this behavior. That's pretty much, it's a one and done kind of deal. We're just getting and we're just setting, and I neglected the consts for all of these things, but you get the point. Okay, so, and now we're ready to define. We've already done this, so here we go. We can go ahead and create that file. There we go. And so let's do the easy part. Get Z, return Z. Set Z is equals value. Okay, this is not as easy because now there is no function for this. Hypot was nice when there was 2 dimensions, but we could use the square root. Do we have square root? Nope, we'll have to include CMAP here again. So give me the square root of x times x plus y times y plus z times z. If you want to put parentheses around these, the order of operations are fairly clear, but if you really want to complicate matters and put things like this just so you feel better about yourself and your life, you can go ahead. And that's the whole function here for a 3-dimensional point in space. What's the distance? It's x squared plus y squared plus z squared square root. And so there you go. So that's that stuff. And now notice again that this is screaming out, just like it did before, there's no default constructor that exists for class .2D. And so we need to fill in, and we need to call our direct parent, which is the .2D class, and it needs one of 3 constructors. Here's the copy constructor, here's the move constructor, and here is the one that we defined. And so you see, I'm going to pass up x value and y value to the 2D, and then from there, the 2D, of course, will set up the y component, and it'll pass the x component up to the .1D. So every part of this, there's 3 separate little cartridges jammed together, 3 little parts, and they each maintain one of the parts of the whole. One maintains the x, one maintains the y, and one maintains the z. Okay, and so nothing here again. And so we've done it. Couple minutes. We've gone ahead and we've set up a whole new class, and this goes back to my PowerPoint slide here. This goes back, not that one, this one, to, where is it here? Let me find it real fast. this one here. This is 0.1D, this is 0.2D, this is 0.3D. It's a straight line, trip through. This is not the best architecture. So once we're happy and we test this out, we're going to try to do something a little bit more like this, where we're going to kind of spread things out a little differently. So we're going to have one boss and 3 subordinates rather than basically one boss or 2 bosses, and depending on the structure, this one is a boss to no one, but whatever, so forth and so on. You get the point. We're going to create a different architecture. Let's go ahead and play with the main now and just incorporate what we already know. So we already know that we can incorporate 0.1D and 0.2D objects, so nothing else should shock you at this point if I include 0.3D. And I can just go ahead, since I've set everything up appropriately, I can put a 3D object into that spot. I've got my 3D, I've got my X, my Y, and my Z position, and everybody's happy because I can put them in just like that. And so for every 0.1D pointer, when it goes down to it, I'm going to print it out, and I don't know what the square root, let's see, so it should be around 7, I would think, 25, 50, a little over 7. I get 6.2 times 10 to the 66th power. So something ain't right. And I know what I did wrong. And so I forgot one little point here, right? So I say, I do like doing this because I make mistakes all the time. I like showing you guys, you're going to make mistakes more than I'm going to make mistakes. But at least you can see that we do make the same mistakes, but we know how to fix them a lot quicker than you guys do, unfortunately. I wish it were the other way around. I wish you guys could teach me some things sometimes. So what happened was, coming back to my 0.3D part, yeah, you probably were screaming at me. I say, were you screaming at me, you idiot, when this was going on? Yes, I took care of the X position, I took care of the Y position, but I did not fulfill my contract. I did not handle the Z portion afterwards, because I did the X and the Y perfectly fine, but I neglected to fulfill the requirements of what makes a 0.3D a 0.3D. And why is this screaming at me? I don't know why it's screaming at me, but it is what it is now, and is correct. And now if I run this, it's a little over 7 like I was expecting, so it was a square root of 50 is what we got out of that. So 7.07, and there I know it's calling the 3D version of that, because it's not, because it would give me 5 otherwise, right? It would give me 3 if it was doing the 1D version, it would give me 5 if it's doing the 2D version, and in this case it would give me this 7.07 if it's giving me the 3D version, and it is. Okay, so that is touching with this. Let me just real quick here add a few more points and just change the numbers around just slightly, nothing crazy by any means. And so now I want to show you something a little more powerful here. And so there's the idea of how would I go, so I can work my way backwards. I can say a 0.2D is a 0.1D. But can I work my way the other way? Yeah, and it's not always true, right? If I could say, like, if I held a fruit behind my back, and I said, I've got a fruit in my hands, you would have to say, and you wanted to know what type of fruit that was, you would have to say, hey, is that a banana? And I'd have to say, nope. And they go, is that an orange? And I go, yep. And so you don't know. You just know you have a fruit, right? Like you say, the compiler, that's why we have to do all the virtualness anyway. The compiler has to figure out at runtime what we're dealing with. It has to do some analysis to look at that and go, banana, or 0.1D, 0.2D, 0.3D. And so that works my way up the chain. But working my way back, there's a possibility, like I just said, where if I ask, hey, are you a 0.2D? And go, nope. And other places you go, hey, are you a 0.2D? And you go, yep. And so this is where everything can start breaking down a little bit because, again, because of the way we've architected our system. But what if I wanted to try to see and only print out the 3D objects? I have a collection of data, but inside of here I go, hey, I want to go ahead and print out only the 3D objects. So right now, what would this look like? This looks like this, 7, 5, 15, 9, 19, 7, whatever. I only want to print out the 2 points that print out in 3D, not 6. I can actually do that here. And so we are familiar with the idea of static cast. So at compile time, we go, oh, this is an integer, I want to convert it into a float, and the compiler will generate the instructions that make that happen. Static, right? So we've been talking about these different keywords today. Static means compile time. What do you think I could do to do a check like this, what I'm describing, at runtime? And so the idea here is dynamic cast. It's the second of 4 C++ casts that we can do. The other two are const cast and reinterpret cast. And we actually briefly see reinterpret cast inside of the binary file lecture video. And then you definitely use this for callback functions and all sorts of stuff out in the real world. But anyway, coming back. So now what I can do here is I can say, I know I have a 1D pointer, right? Because I'm screaming this out. I know they're 1D because everything's 1D. But now I have to say, okay, fruit, are you banana? Or I have to say, okay, point 1D, are you point 3D? And so in this case, I can try to cast, and I'll use R instead of whatever, and I'll just say, okay, equals dynamic cast, and you can only do this for pointers, or references, I suppose. And I could say, okay, try to take P, which I know is a 1D pointer, and try to turn it into a 3D. Try to work your way down to see if you can get there. And if you can, it will return a pointer, and now I can treat this object, I can put an R here, and I can treat this thing like a 3D object. But if it doesn't work, if this doesn't work, it will return a null. It will return null pointer, and I can't use it because it said, nope, it's not a point 3D. So this will crash. Because I was trying to allocate, I was trying to use a null pointer. The first one here, trying to hit the 1D object, it said, are you a 3D? And it goes, nope. And so, so immediately, you can see it, immediately say, okay, are you a 3D? And it comes back as 0, null. And then I'm trying to access something, I'm trying to access data from null, and then it immediately throws up on me. So I would have to put an if statement around this to say if R does not equal null pointer, then I can go ahead and print. I still want to delete it because no matter what, if it's a point 1D, point 2D, point 3D, I'm deleting it as I go just to make sure that my news and my deletes match up so I don't have a memory leak. But at the end of the day, I only want to print if this thing is a 3D object. And so now, there we go. Now I only print the two things out, the two things that derive to point 3D. And so coming back one more time to this, it's kind of cool here to say, now I have two distinct pointers to the same object that can treat them in different ways because I've done my due diligence, I've done my testing to make sure that everybody's happy. Because what I can do here, if I say, if you see P arrow, because it's a pointer, you can see I only can access it as a point 1D. There's the Destructor point 1D, there's get X, set X, distance to origin, it's all I've got. But what if I do the same thing with R? You can see all the extra stuff. I have Destructor for 1D, because that's still base class stuff, but you can see I get the X's, I get the Y's, I get the Z's, I also get a newer distance to origin function. And again, it's all overloaded and it's all virtual, so everything works out just fine. And so it knew to print the correct stuff out. So that's how you go ahead and work your way backwards from the top. You can always work your way up the chain because point 3D points to point 2D, which points to point 1D, but it doesn't work the other way. All point 1D knows is of itself. It doesn't know that other people are deriving. It doesn't know it has children. It's one of those, like a real world, weird Maury Povich real world example. Point 1D doesn't know it has a child, but point 2D and point 3D knows it has a parent, and it knows who it is. And so basically you have to scream out, hey, what are you doing here? You're my parent, and work your way back. Are you my parent? Yes, you're the father. No, you're not the father, kind of thing. Okay, so that covers dynamic cast. So the last thing I want to do before we cut this video off here is to discuss re-architecting this point structure that we have. So I'd say most people would look at this and then they're perfectly happy with the way everything is set up. But the one thing I can do to break this just slightly and be a little pedantic or whatever is, what if instead of wanting point 3D objects, what if I wanted point 2D objects? And so you would just run this and you'd be like, okay, cool, let's run this. And what comes up is 4 separate values. And so this is not good, right? Because of the whole way the ISO relationship works, because we've discussed. So anything that derives into point 2D is considered a point 2D object. And so, oopsie, yeah, this isn't working out for me because point 3D then is a point 2D. So anything of those 2 separate types work out to be exactly the same. And so that's why it prints out both 2D and 3D in this case. And so we haven't done anything wrong. Like the programming is perfectly fine. Everything, we've been following best practices on the programming end of things. And now the final step would be to come back and take a look at this and figure out how to re-architect the entire structure of the inheritance to make this and change this. So I don't have to change this code. I can refactor everything on the header side, and then this is going to work for me, and it'll actually only give me the point 2D side of things. And so it'll only give me the 2 objects that are point 2D. And so again, a lot of times you're going to notice out in the world, there's many, many ways, maybe even already with your homework assignments and things, there are many ways to do whatever it is you're asked to do. And so when it comes down to it, finding the best way isn't always an easy, and sometimes there isn't a best way. Sometimes you just have to go with a way and just suck it up and deal with the positives and the negatives of that. And that's what we're going to get across here. Okay, so we have our 3-point system set up here. We have our point 1D, we have our point 2D, and we have our point 3D. And so now we're trying to figure out a way to make this, to architect this a little more nice. And you're going to need this for your homework assignments. Those of you who have me, especially depending on what year this is, the Boov versus the Gorg assignment. When it comes to, I have my Boov, I have my Gorg. Now it's time to create this, this base class that incorporates both of them. And it's the same idea here, where I'm saying, okay, so what is similar and what is different for every one of these classes? And so it's tricky. And so you say that you can see if this isn't worth the effort to you, then yeah, I guess it's not what I'm about to do here to make this thing work, then don't go ahead and follow it. But this, because the duplication of code, I mean, things get a little iffy here. Things get a little weird. And so what I want to do then is figure out, okay, the get functions for point 1D, I'm going to need that for point 1D, point 2D, and point 3D. I need the x coordinate. Okay, fair enough. And so then if I'm going to create a master class that works over everybody the same, everybody has an x. So I might as well just push this up into this master class. And so we're actually going to need a 4th one here. I'm just going to call it point. Point.h. Where does it go? It goes over there. Let me see if I can. I've never done this with 4 files up at the same time. Okay, let's see. There we go. All right. So, but just coming back to this here. So now thinking about this class point. So we're technically kind of making it so that everything point 1D is going to lose a lot of its stuff here because this comes along, but it's all common again. It's what's common to everything that you derive from. And if I derive into a 4D and a 5D and a 6D, I'm going to need that x. And so there's my double x, there's my get x, my set x. I'm going to need a constructor and a virtual destructor. Let me just copy that one over. So I've got point that takes the value for this x component. I've got destructor for point, because it's going to be virtual, because this is now going to be the master base class for all 3 of these different points. I'm going to have point, and then every one of them is going to point in, as opposed to having a vertical structure. It's going to be more spread out. Okay, so I don't need this virtual destructor anymore, and I need a custom constructor for point 1D, and I need this virtual function for distance to origin. And so now this is the key here also. This is what is common to every one of these classes, is this x component. So I've just shifted everything, the x component, from point 1D up. Okay? So now the question is about this other stuff here, this last function, this virtual function. Oops. Everybody uses it. right? And everybody uses it. Everybody uses it differently. There's no base behavior, right? There's none of these two will, or anything, if I create 4D, 5D, 6D, and beyond, none of them will ever share the same behavior because it'll always be different. And so since this will always be different, there's no reason for me to define it here in just that base point class. Because every point 1D is going to have a different version, point 2D is going to have a different version, point 3D is going to have a different version, and so forth and so on. And so this equals 0, coming back to the PowerPoint, that's the whole idea here. This is called a pure virtual function. It's a member function. It's a virtual function that must be overridden in a derived class. So I'm basically saying there is something called distance to origin, but it's up to anybody who derives from me to define what that means to them. And we've already done the work. It's just, again, a matter of re-architecting this system to make it work with that description. And the equals 0 is how you go about doing that. I don't know why that is, why it's not a keyword or something like that, but that's the way it is. And you must have no function definition. So I'm not going to define it here. When I create everything in here, notice it's in turn, there's no green squiggly for it. There's no reason to define it here. Okay, so let's go in. How does this affect everything else? So let's go in and set up these 4 functions. Let's define them. I know this is getting complicated. Let me just, let's eliminate the point 2D stuff and the point 3D stuff for now and just focus on point and point 1D. Okay, here we go. So then, where's my point.cpp? Okay, here we go. And so this is basically the exact same stuff as point 1D, right? Because we're just shifting responsibilities right now. And we'll fix all this up in a minute. Let's just do point itself and work our way back. So point will set up the x value, and it'll set it up with value. Just like I see here, there's nothing here. All right, the destructor does nothing as well. It's only there because I need to have a virtual destructor defined for the base class. And so there's no dynamic memory in any of these classes, so I don't have to worry about any extra work. Starting next week, or next class with the vector class, and when we create our own custom class, we will start putting stuff inside of the destructor to make sure that we destroy the memory we've newed up. And you'll see that it gets more complicated as we move into more complex data structures. So x is equal, it's like we're just doing the same exact stuff here as we've done prior. And again, if we were doing this for real with the knowledge that we now have, we would be doing this from the start. Or at least most of this from the start anyway. Okay, so now that handles point. We've got the x point, we've got the destructor, we've got the constructor, and so now point itself is back to normal, or is normal, and so now we can re-affect this and say, okay, there's nothing here but a constructor for point and this virtual function, and now it's an override. Am I not allowed to do that? Hold on, let's see. Member function declared with override does not override. Okay, I just haven't done it yet, I guess. I thought it would be green, but now it's red because it can't find it. Okay, so now coming back to here, we get rid of this get in the set because we've done it over here and we're deriving from that. Or, excuse me, I have to make sure I derive from that here. Public point. I'll need to include point.h. Okay. All right, there we go. And those are the only 2 functions that matter now. And so, yeah, destructor, don't need. Distance to origin, there we go. But now here's the, so this is the fun here. X, did I make this protected? I made this private. Let me make this protected. So everybody, because I'm a base class, everyone can derive and steal my X. And now this is put back to normal. But now this is wrong here, the constructor, because X is a non-static, blah, 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 blah. And I just need to call point and pass the value up. Because this constructor needs to call this constructor, and so the value gets pushed along and put into the X value. And now, isn't that interesting, right? Like all of the X stuff is still part of point 1D, but it's now put into this point class that everybody can access. Okay, so Fair enough. We have ourselves working on something nicely here. So to finish this, I'm only going to work with point 2D. I'm going to leave point 3D alone, and then we'll remove it from the main when we show this thing working and just figure out just the slight little thing we have to do to main. We're going to do all this hard work, and there's very little we'll have to do to main to bring everything back and make it work. So now coming in, let's take a look at point 2D.h, point 2D.cpp. Let's look at them both over here. So coming back at it here, point 2D no longer is parented to point 1D, it's parented to point. And so now all of this changes. So I need an x and a y value. I do need the get and set y. I am still overriding this. And I still need a protected double y. So yes, nothing really has changed here. The only real change is, in the function, I'm overridden this function for the virtual function for distance to origin. It's correct. The set, the get, I just have to pass this up to point, set my y value, and look at that, it's done. Like, I've refactored this thing because at least for this refactoring, not much has changed between point 1D and point. Just maybe the name and just that's it, right? So this all works out perfectly fine now. And now let me rebuild this just to make sure it comes up successful. I guess I can't read that ready. Oh, let's see. As long as it comes up, and then yeah, let's not worry so much. And again, I'm going to get rid of the point 3D stuff just for this example. I'm just going to remove it from our code base. Remove, because I just want to focus on just point 1D versus point 2D. Here are those warnings that I haven't been able to figure out yet, and now we're back to main. Okay, so now coming back to it, I do not need all this. I need to include point. And now I can say I have a vector of point objects. And so this, and I believe everything else will work now. And I can let me get rid of the 3D stuff here, like I was saying before. So we can just focus on this. And so now when I print this, I'm going to say, okay, there's a point 1D, a point 2D, a point 1D, point 2D. Only do point 2Ds, it prints the 2Ds. And you're like, okay, but you got rid of the 3Ds. Okay, fine. Let's try 1Ds. Because before, by saying print all 1Ds, it would have printed everything. Because 2Ds are 1Ds and 3Ds are 2Ds, which are 1Ds. So a minute ago, or before we did this refactoring, this would have printed all 4 out, and then it printed 2 out for 2D, and it should just print out 2 for 1D as well. And it does. Just the 7 and just the 9, just the ones that derive into point 1D. And so I've refactored. I've refactored point 2D and point 1D such that basically I have point, and then I have both point 1D and point 2D point in, so they're distinct elements. And so now all of that work got me so that since they're distinct elements, I can't find it here, dynamically casting to them will not work it to a point where they're both the same thing. And that would work for 3D and 4D and 5D and beyond, that because they're all coming from that base point, that basic point there, from point and deriving from it, they're all going to be distinct rather than having that vertical structure where point 1D incorporates everything, then point 2D incorporates everything but not 1D, and so forth and so on, so you can get the correct dynamic casting and the correct behavior of the objects that you want. So this is more important out in the world because, yeah, for very specific objects, I'm going to want very specific behaviors. And so if I'm accidentally pulling in objects of different types and making these things not work like they're intended, then I'm going to have some weird side effects, and someone's going to have to come back and fix that code later. Wouldn't you rather fix it up first time while you know it's a problem, and use that part of your toolbox, then go back and fix up that plus everything that changes? How does that cascade against the rest of your code base? That is something that a lot of times you do not want to face when you've got a deadline, because anything you touch near the end of a deadline could break other things, and it could introduce other bugs that you find later, hopefully not when you get out into production. All right, so that is everything there is to worry about right now when it comes to polymorphism, inheritance, virtual functions, dynamic casting, all of that jazz. We've done it all in this hour and 10, hour, 15 minutes, and hope you learned a lot. But as always, if you have something I said wrong or you have some questions, send them to swardb@cud.edu, comment here on YouTube, and I'll get back to you as soon as I can. All right, so those of you in our advanced C++ class, we are now moving on to the standard template library. And so we're going to be moving on to exception handling. And we're going to be moving on to templating and getting ready for the vector class, both checking out how the vector works in the standard template library and checking out how to make our own custom version. So look forward to seeing you in those videos. Take care, everybody. Have a nice day.